Swayam Prabha. Digital India. Educated India.
I am Divendra Chaturvedi from IIT Madras. Surprised to see very low audience. Probably after lunch, many are returned. So let's start with today's presentation. We have Tanuj Karia, who is from Imperial College London. So he will be presenting assessing the performance of artificial neural network for enforcing visibility in optimization based design of solvent mixtures.
Thank you, Professor, for the kind introduction. Hello, everyone. My name is Tanuj Karia. Good afternoon to you all. I hope you are not sleepy after the lunch. What I'm going to talk about is using neural networks to check for miscibility when designing solvent mixtures or optimization-based methods. So first of all, as chemical engineers, we all know that solvents are really important. They are ubiquitous and they are used widely in separation processes such as absorption and crystallization. Also, in many cases, we found that mixtures of solvents actually perform better than pure solvents, and I would like to show that using an example. So if we consider a very common drug, paracetamol, Granberg and Rasmussen conducted experiments on solubility of paracetamol in a water acetone solvent mixture, and as you can see from this plot, like solubility in a 30-70% water acetone mixture is at least 5 times higher than either pure acetone or pure water. So there's potential for enhanced performance. However, there's one challenge. When we want to design solvent mixtures, it is a combinatorial problem. So I would like to just show that when we just consider, let's say, an 18 predefined list of solvents, and we want to select up to 3 solvents from those 18 solvents, and you can see that there are 1,000 possibilities that we need to check for. And in addition to this, another sort of level of combinatorial complexity is that you also need to decide the proportion of each constituents in the mixture. So we have a large combinatorial space that we need to explore. Luckily, and you might have heard Professor Ghani talk a lot about this on Sunday. There are systematic approaches to explore this combinatorial space, known as computer-aided mixture or blend design, or CAMD in short. I'll just quickly explain what CAMD is again. So we start with a set of atomic groups, and we play Lego with them, and we use something called group contribution methods to link the structure of the molecules with its properties, and then we formulate an objective and an optimization problem to get the identity of the optimal mixture and its composition. And we can run this model or solve this model several times to obtain a ranked list of promising mixtures, which we can then verify experimentally to design better processes or better products. So just to summarize, Professor Ghani and co-workers define CAMD as given a set of molecules, a mixture with the desired properties that optimizes a given performance measure. So one important thing to consider when we design solvent mixtures is that that mixture exhibits a stable single liquid phase. So we need to check for miscibility. So what we essentially want is a single layer of liquid rather than it separating it out in 2 layers. And there are some ways which we can do this within the CAMD approach. So one common approach that is used is by imposing a constraint, which I call the sufficient condition. And it's based on the second derivative of excess Gibbs free energy with respect to the composition of the solvent in the solvent mixture. So good thing about this is we can very easily add this constraint to our problem formulation, and it prevents the design of immiscible mixtures to a certain extent. I say to a certain extent because this is only a sufficient condition but not a necessary condition for miscibility. The disadvantages are that it is only applicable for binary mixtures, and it makes the optimization model very challenging to solve. Another way that we can check for miscibility is by doing some sort of a post-optimization analysis. So once we get the optimal solution, we can quickly check whether the phase is stable or not. So this is very easy to implement, but this is not ideal because if it is not miscible, we might have to change the conditions of our problem or the model, and it requires re-optimization. So another way that we can check for miscibility is using something called tangent plane distance. And I say this is a more rigorous approach because this is both a necessary and a sufficient condition to check for miscibility. So tangent plane distance can be formulated as an optimization problem as shown here, and I'll explain what this is. So in this problem, we are trying to minimize this function f dpt of x, which is shown here. And in this function, we have xi, which is the trial phase composition of the component I in the system. Then we have gamma I, which is the activity coefficient of the component I in the system. And we have zi, which is the composition of component I at which we want to test the phase stability. So we have this optimization problem. Looks very innocuous, but it's not. And geometrically, we can interpret it like this. So this is the plot for Gibbs free energy for heptane methanol mixture at 0 degrees Celsius using the NRTL model. And on the x-axis, we have the mole fraction of methanol. So in this plot, we are trying to test for phase stability at the composition of 0.17 of methanol. And what we do is we draw a tangent to the curve of Gibbs free energy. And as you can see in this curve, it intersects the curve for Gibbs free energy, the tangent. So at some point, the distance between the curve and the tangent is negative. So in this case, this is unstable. So it would split in two phases. On the other hand, if when we draw a tangent and if the distance is positive everywhere, of course, except at the point that we are checking for phase stability because that is trivial, then it is absolutely stable. Another possibility is that we might have an equilibrium condition where the tangent has two common points. So that gives us the equilibrium compositions. So this is all good. One problem with this is this involves solving a non-convex problem to global optimality. So this is prohibitive because within CAMD we are already solving a very challenging problem to optimality. And if we are to use this, we have to solve another problem to optimality inside a challenging problem. So that's not really useful. So what our idea is that we use a data-driven approach to do these phase stability calculations based on TPD and then incorporate it within the CAMD framework to check for miscibility. So as with any data-driven approaches, the first thing we need is data. So what we do to get this is we use an open source package called PhasePy, which is developed in Python, and it does fluid phase equilibrium calculations, and it has a routine built in to do the tangent plane distance calculations. So what we do is we take a list of solvent mixtures that we are interested in, and for each solvent mixture we generate a large amount of points which correspond to the composition of the components in the mixture and the temperatures that we are interested in. And then we run the TPD routine within PhasePy to get the data on phase stability. So once we do that, once we have the data, we need to train our model. So to train the model, first we need to decide what our inputs to the model would be. So the inputs would be the identity of the solvents, the composition of each component in the mixture, and the temperature of the process condition. So here, I would like to point out one important thing, that identity of a solvent is a discrete choice. So usually when we have to train machine learning models for such discrete choices, we need to do one-hot encoding. But in this case, I would also like to inform you that we are always using UNIFACT to do our calculations, UNIFACT thermodynamic model. And with UNIFACT, we can parameterize the identity of the solvent based on the van der Waals surface area and van der Waals volume parameters, or Q and R parameters as they are called. So they are used to sort of identify a particular solvent. So those are the inputs, the composition and the temperature. Once we have the inputs, we train the ANN, and the ANN is a classifier, and this classifier would give us the probability whether a solvent mixture is miscible or not. So once we have that probability and this model, what we do is we take this model that we trained, we embed it in the CAMD optimization model, and we set a constraint saying the probability of miscibility should be greater than some lower bound on miscibility that us as a user we need to decide. So now the next question which comes is, how do we decide about choosing this lower bound? So first I would quickly like to introduce what accuracy is. So accuracy tells us what fraction of model predictions are actually correct. And what I'm showing here in this plot is on y-axis we have accuracy and on x-axis we have probability. So let's say if we just choose a probability of 0.1, so this probability of 0.1 is actually the threshold at which we say the model, the mixture is miscible or not. So for example, if it is less than 0.1, then the mixture would be immiscible, and if it is greater than 0.1, then it would be miscible. And if you choose that probability, we would get very low accuracy. So we would misclassify a lot of samples. So what we try and do is we try and look for the maximum accuracy, and we use that probability value as our lower bound. So now we've sort of understood the methodology. Now we would like to try out whether this works or not. So we've used 2 case studies here. And again, Professor Ghani spoke a lot about these case studies, so I'll go very quickly through it. So the first case study that we consider is we want to design a solvent mixture that just simply maximizes the solubility of ibuprofen from a predefined list of 9 solvents. So I would like to show you the problem formulation, and this is a problem formulation with the sufficient condition that I had shown you earlier. So here our objective is to maximize the solubility of ibuprofen, and then we have some constraints which are linked to solvent selection and assignment, which are linked to the set of binary variables y. Then we have this equation which gives us the solubility of ibuprofen related to solid-liquid equilibrium. And you can see this is dependent on the activity coefficient of ibuprofen. Then we have the miscibility mole fraction, and based on the miscibility mole fraction, we have the sufficient condition. And again, this sufficient condition is based on the activity coefficient or partial derivative of the activity coefficient of the solvent. And these activity coefficients are obtained using the unified thermodynamic model. So this is the original problem formulation. Now with the classifier, the problem formulation remains more or less the same. The main difference is here. So instead of using the sufficient condition for checking for miscibility, what we do is we embed the ANN in our optimization model, which gives us a probability, and then we set the lower, like the constraint on probability as shown here. So as I said, we choose the probability with such that the model operates with maximum accuracy. So in this case, the lower bound on probability was 0.47. Another point which I would like to point out is that for each case study, we repeated the methodology that I had explained earlier. So for each case, the lower bound on probability would be different. So moving on to the results, we tried to solve this problem with a global MINLP solver skit. And there are 2 parts to this case study. One where we select exactly 2 solvents. And here in this plot, what you see is the solvent blends ranked according to the solubility of ibuprofen. So I'll explain the identity of these labels here. So for the model with the sufficient condition, we have these 1 to 5 blends. And with the classifier, we have the 2 to 6 blends. And these are the identities as shown here. So now, just because we are testing this methodology for the first time, we want to verify the solutions that we obtained. So what we did was we tested these solvent mixtures in phase-wise separately for stability, and we found that the solvent blend 1 was actually unstable. So even though it is more promising and can dissolve more ibuprofen, but it is not actually realizable in practice, so it's sort of useless. And with the classifier, we can sort of avoid that solution and not get misled. So as you can see, the probability from the classifier was quite low, but for the others, we have quite high probability of miscibility. So now moving on, the second part to this case study, which is selecting up to 3 solvents. Here again, I would like to point out that if we use the sufficient condition, we have to sort of take pairwise condition of the sufficient condition to check for miscibility, and each pairwise condition has to pass the check. So that increases the complexity of the model a lot. But when we use the classifier, we just need one ANN, which we can embed in the model, and we can check for miscibility. So it reduces the model complexity a lot. And here is the result that I got. So with the classifier, we got the global optimal solution, the methanol chloroform mixture. With the sufficient condition, we reached the maximum time limit. So probably this solution is still valid, but since the problem was very complicated to solve, the solver could not come up with a better solution in the time limit. So, which brings me to the next part, which is the cherry on the top, the computational benefits that we obtain. So in this plot, what you see is the wall time on y-axis and each integer cut iteration on x-axis. And the blue bar represents the model with the sufficient condition, and the red bar represents the model with the classifier. As you can see, the red bars are much smaller than the blue bars. And we see a much more drastic improvement when we select up to 3 solvents. So this timed out in 10 hours, but we solved this classifier embedded model in around 2.5 hours. So it's a very significant reduction in solve time for solving these problems to global optimality with scale. So this was one case study. We want to build on this case study. So this second case study also takes the process level decisions into account. So you want to design a solvent mixture now which maximizes for hybrid cooling and anti-solvent crystallization of ibuprofen. So we consider the crystallization process. Again, Professor Gani spoke a lot about this, so I'm going to quickly skip through. But I would like to explain the mathematical formulation. So this bit is the same, similar to previous case study. One major difference being here temperature is also a decision variable. Next, here instead of just maximizing the solubility of ibuprofen, we want maximum yield of ibuprofen at the end of the process. So that's our objective. And then we have some mass balance constraints, some operational constraints on temperature and so on. And here the lower bound on probability was set as 0.46. So now looking at the results, in this case, we could not solve this model to global optimality with skip because it took really long and it did not converge. So we just used a local solver for SVB with Conopt as the subsolver. And here are the 5 promising solvent blends that we obtained. So SC represents the sufficient condition and classifier is the classifier embedded model. And we can see we obtained the same set of promising solvent mixtures in this case with very high yields. The only slight difference being some difference in the process conditions for one propanol water mixture that we got, but the yield is the same. Now I would like to present a further challenge, which is the effect of solute. So again, we verified in the same manner the solutions that we obtained using phase pi, and here you see this is the column for just the binary solvent mixture, and it passes the check within phase pi for phase stability. And here are the probabilities that we obtain with the classifier. However, it is found that in the presence of API, it sometimes shifts the boundary of liquid-liquid equilibrium for a solvent mixture. So we need to account for that as well, which we haven't in the classification model that we trained. And you can see in the presence of ibuprofen, all of these solvent mixtures are not realizable in practice. So one good thing about our approach is that we can easily extend it to multi-component mixtures, including the to also include the effect of ibuprofen, which I'll talk about. We haven't done it, but it's part of future work. But just to conclude and summarize, we've shown that we can embed a classifier-based model to design solvent mixtures. And one very good advantage of this approach is that it provides the person who's in charge of developing the process with an interpretable metric, which is that whether a solvent mixture is miscible or not. So it gives us a probability rather than insufficient condition. It just gives a number which we cannot really understand. And we also showed that we can identify promising solvent blends which have a high probability of actually being realized in practice with lower computational effort. And as part of future work, as I said, we want to model the effect of presence of solid on miscibility of solvent blends. We also want to compare the performance of different sort of classification models such as support vector machines, decision trees, etc. in an optimization context when we check for miscibility. And finally, we would like to test on more industrially relevant case studies with the references shown here, where they account for end-to-end process design and solvent blend design. So I would like to acknowledge all of these people, and I would like to thank you all for your attention, and I'm more than happy to answer any questions.
Thank you, Tanuj. So now floor is open for questions.
Your solvents in this case are water and other simple molecules like you've shown here. What if the solvent is a slightly longer chain molecule like a lipid? Can the technique still be used?
So that would depend on whether UNIFAC can model, because all of our data is generated using UNIFAC. So if UNIFAC cannot model, we can use some other thermodynamic model to generate our data. So in that sense, it would be flexible. So yes.
So any other questions?
You have assumed that immiscibility is no good, but in some cases, immiscibility, if you have a solvent that is miscible, but it can separate into two phases under conditions that makes your recovery much better, much easier. Okay? Can you formulate something into this?
So we can do that if we know that we desire that the solvent should separate out.
With some disturbance in conditions, let's say raised temperature or something like that.
No, so if I understand your question correctly, what you are suggesting is that in some cases we might want immiscibility in solvents. Right? So we can easily adapt our model in that case just by flipping the sign of the inequality constraint and look for immiscible mixtures rather than miscible. I hope that answers your question.